Hello guys, this video is on closed graphs. Hello guys, this video is on closed graph theorem. The closed graph theorem, it is one of the fundamental theorem of functional analysis. This theorem, it gives criterion for the boundedness of an operator T, and the proof of this theorem is an application of the bounded inverse theorem, which we discussed in earlier video. Now the closed graph theorem, it states let x and y are Banach spaces. Like we discussed in earlier video, for the fundamental theorem, Banach space is necessary. And if T is an operator from dt to y, where dt is subset of x, and if T is a closed linear operator, closed, this is the criteria, then if dt is closed in x, then T is bounded. Like I said earlier, this theorem, it gives the criterion for the boundedness of operator T. Now let us define the closed linear operator. Here the operator T is closed if its graph GT is closed in x cross y. If its graph is closed in x cross y, then the operator is closed. Now let us give explanation to this statement. Now first let us define graph of an operator. So graph of an operator, it is the generalization of graph of a function on plane. On plane, if this is the function and then this is the graph of the function, then this graph, it is nothing but the set x and y, where x is an element of domain and y it is the image of the domain. Actually graph is the set x cross xy. It is the set of order x y. Similarly, for the operator T from dt to y, its graph is the set gt, which is the set of order pair xy, as such that x belongs to domain and y it is the image of x. So this is the graph of the operator T. Now let's move on to the proof. So as I said earlier, we prove this theorem with the help of bounded inverse theorem. We apply bounded inverse theorem. So let's move on to the last. To prove this theorem, we defined a operator P. We define an operator P from gt to dt, and to apply the bounded inverse theorem, we need, bounded inverse theorem is also fundamental theorem. So to apply this theorem, we need the domain and codomain, both Banach spaces. We need these two spaces complete. So first we show the spaces gt and dt are complete. That is our first task. Now I have given the background of the proof. Let's move on to the proof. So step 1, first we show the space x cross y is complete. Now given x and y are normed spaces, x cross y is also a normed space. Under the norm, we have got norm of x y, order pair xy is the sum of norm of x and norm of y. So we have defined a new norm on x cross y, and under this norm, the space x cross y is a normed space. Now we show this space is complete. For that we take a sequence Zn, which is Cauchy in x cross y, and we show Zn it converges on x cross y. Since Zn is Cauchy, then for a epsilon positive, there exists a natural number n, such that for all m n greater or equals to n, we have Zn minus Zm is less than epsilon. Now Zn is xn comma yn, Zm is xm comma ym. After simplification, we get xn minus xm comma yn minus ym less than epsilon. Now this step is important. We apply the definition of the newly defined norm on x cross y, then we get this step. Now since the sum is less than epsilon, the individual positive part is also less than epsilon. This shows x and yn are Cauchy sequences in x and y respectively, but x and y are Banach spaces, complete spaces, so there exists x and y such that xn converges to x and yn converges to y. This shows Zn, which equals to x and yn, converges to xy, which is an element of x cross y. This shows Zn, which is Cauchy sequence, converges on x cross y. This shows the space x cross y is complete. Now second step, T is closed is given to us. By definition, its graph GT is closed on x cross y. Now since closed set of an complete set is complete, we have GT is complete, and since dt is complete, dt is closed is given to us, dt is also complete. So we have got GT complete, dt complete. Now we consider a map P, which is nothing but a projection map on x. We may consider a map P from GT to dt, which is defined by P x comma tx equals to x. This is the projection on x. So this is the x comma tx. Its projection on the x-axis is the point x. We defined a projection map P from GT to dt. GT to dt. Then we can show that P is linear map. Clearly P is linear map. P is also bounded map, and P is also bijective map. So since P is bijective, P inverse exists. Here P inverse from dt to gt, it exists, and since dt and gt both are complete, and since P is bijective, we have made the criterion of the boundary inverse theorem. By the application of boundary inverse theorem, P inverse is bounded. Since P inverse is bounded, there exists a positive integer m greater than 0 such that P inverse x is lesser or equals to m times norm of x. And finally, norm of tx is lesser or equals to norm of tx plus norm of x, which equals to norm of x comma tx by the definition of our newly defined norm, and this equals to P inverse x. Norm of P inverse x from 3, norm of P inverse x is lesser or equals to m times norm of x. This shows norm of tx is lesser or equals to m times norm of x. By definition, T is bounded. So closed graph theorem, it states if T is closed and dt is closed in x, then T is bounded, and we have proved the theorem. Thank you.